So in this lecture we will learn how to compute the sample size for proportions. So we see that there are many cases, but we will group them into smaller groups. So we have some of the cases are related to one sample, either whether we want to compute the proportion interval or we want to construct a test, or we will construct a proportion interval or perform a test on a proportion, and we will distinguish between large populations and small populations. Then we will have another group in which we are using two samples and we want to construct a confidence interval either on the difference, the risk ratio, or the odds ratio. Then we will also have another group with two samples, but now we will be doing a test and we will have the Fisher's exact test and then multiple approximations. And the last group will be some more advanced topics in which we have paired proportions or we have equivalence tests with one samples, two samples, or C samples. So let's start with the first group, in which we want to construct a proportion interval for one sample. So let's say that you're developing a new vaccine, and in this new vaccine you want to construct a confidence interval on the proportion of animals that get infected, and this proportion of animals will be P, and you want to construct a confidence interval that goes from 0 to PU. So let's say that we expect that no more than 1% of the animals get infected, but we want to construct the confidence interval to contain the true proportion value with probability 95%. And then let's say that we study N animals and X of them get infected. If the probability of infection is this upper bound here, then we know that we would observe X infected animals following a binomial distribution. So this would be the calculation that we would need. This is N over X, and then this is the probability of success meaning getting infected, and times the probability of failure. So, given an example, let's say that we study 300 animals, and the probability of infection is this upper bound 1%. Then we would see 0 animals in 5% with probability 5%. We would see one infection with 50% of probability, and then 2, 3, 4, and it would be very unlikely to see 15 animals infected. If we see 15 animals infected, it is because the probability of infection is much larger than 1%. So given that we have observed X animals, we want to find a probability of infection. So we want to find the upper bound such that all this area up to X, that is the value that we have observed, all this probability is 1 minus alpha. So this is more or less another way. It would be saying that from X to the right we see alpha. Okay, so we can obtain the smallest n that is obtained when X is equal 0, and then we can calculate n. This is an exact, there is no approximation here, so n can be calculated like this. But equation X, this equation 1, is valid for any X, and if X is larger than 0, it is not so easy to solve. But if X is much smaller than N, so let's say that we observe 300 animals and only 1 or 2 get infected, then we can use the fact that with this proportion, this is the proportion that we have observed in our data, so this p-value is distributed as this chi-squared distribution, and this chi-squared allows us to compute n, and then, for instance, if X is equal 0, then we can calculate n in this way, and this is the famous rule of 3, because for instance, this chi-squared, let us look at it. So we have 1 minus alpha, this is given, and this is 2 divided by 2 times the upper bound. But all these, except for the PU, all this ratio is 2.99, and so we can approximate by 3. So there is a rule in epidemiology that says that if you want to study a process that has an upper bound of, let's say, 1%, you should study at least this 3 divided by the upper bound, that it gives you around 300. The exact method is given also 299, so we see that this approximation is pretty good. Okay, so let us give another example, but now the proportion will not be close to 0. So the proportion that we were trying to calculate before, it was close to 0, and then the confidence interval was of the shape 0 and then an upper bound. But let's say that now we have a problem in which the proportion is not close to 0. So we want to find an upper bound with we want to construct the confidence interval with a lower bound than an upper bound, and we want this confidence interval to have a precision of 0.02. So meaning that the difference between the upper and the lower bound is 2%, and we expect the proportion to be around 15%. So yeah, so we want the problem is we want to compute what is the proportion of heavy smokers, and heavy smoker is defined as smoking more than 5 cigarettes a day, developing lung cancer between the age of 40 to 50 years old. And we know that that proportion should be around 15%, but we want to construct this confidence interval such that the difference between the upper and the lower bounds is smaller than 2%. Okay, so yeah, so every time we randomly draw an individual, so a smoker between 40 and 50 years old, the probability of having developed the lung cancer would be around 15%. So for instance, here we see that smokers, the population is this one. The proportion of smokers is around 30% of this. So we have 30%. We have 2 million of people between this age, and the number of lung cancers is around this one. Okay, so if we study n individuals, again the probability of observing X lung cancers is given by a binomial distribution. So for instance, if we study n equal 20, the probability of observing X lung cancers when P is 15% would be distributed like this. So we should see the most likely value is 15% of 20, that is 3. So this is the most likely value, and then, but it wouldn't be unlikely to observe values between 1 and, let's say, 6, even if the true proportion is 15% and the most expected value, or the expected value and the most likely is 3. Okay, so let's say that we have this result. So we studied 20 people, we observed 3, so our estimate of the proportion would be 0.15, and then the confidence interval has to be found in such a way that from the lower bound to the right, there is alpha half, and from the lower bound from 0 to the number of observations for the upper bound, that is also alpha half. So given so you have to find PL and PU, because n and x, this is an experiment in which we have observed capital N people, and we have seen X, capital X, cancers. So you know n and x. Small x is a dummy variable for the summation, alpha you know, so all you need is PL and PU. So you can calculate PL and PU, and for this experiment we see that the PL and PU are this one. So even if you have seen 15%, the confidence interval is pretty large. So our constraint before was that this delta is smaller than 2%. So what we can do is use these equations to calculate the x. So now we know that how to calculate PLPU. So we can make that PLPU is a small, the difference between the two is smaller than 2%, and then we need to calculate the n. So the exact solution. So if you have one-sided confidence intervals, so not test but confidence intervals, you have a confidence interval of the form 0PU or PL1, then the equations are a little bit different, but not so much different. And yeah, I agree that solving for n in this kind of equations are really difficult. So are there approximations? In reality there are. So we can use the normal approximation. So the normal approximation can be applied when n times p is larger than 5 and n times 1 minus p is larger than 5. And this normally happens for p's within this range between 10 and 90%. And then if that happens, then this calculation is distributed as a 0-1 Gaussian. And that translates that P is distributed as this thing. That this is a relatively famous result in statistics. And yeah, so our problem is estimating P such that the confidence that is within this range plus minus delta, and then you simply have to solve this equation here. So you have n, and we see the classical result of the Gaussian. So you see something that depends on the confidence interval, the level, the confidence level, and divided by a normalized effect size. The normalization in this case is delta divided by this square root. Okay, so here in our example we wanted delta to be 0.02, and we expected the proportion to be around 15%. So that gives us 1,000, more than 1,000 smokers, and we need so many because we want it to be very precise. Okay, so what happens if the population is not that large? We had millions of smokers, but if our sample size is smaller, then instead of millions we have thousands only. So let's say we have 10,000 smokers, then our sample size is larger than 10% of this population, total population. So we don't have such uncertainty around the proportion. So if you measure, the larger the proportion of the population that you measure, the less uncertainty you will have on what is the true proportion. So you can correct for that, and this is the correction. So n prime, that is the new sample size, will be the n for the large sample size. So this n is the one coming from this approximate calculation, and divided by 1 plus minus this thing. So for instance here we see that we reduce the sample size from 1200 to 1100. So just a small reduction, but we don't have to sample so many. And yeah, so what if we want to construct a test on that proportion? Okay, so let's say that you are studying a kind of disease that is called the tenosynovitis of Decker-Van, and then this is also called the blackberry finger. So people that are texting some quite often, they have a problem in their fingers. And you know that in the general population, this proportion is around 1%, and you suspect that people that use the smartphone quite heavily, the proportion of this problem in the fingers could be higher. So you want to have a statistical power of 90% if this proportion is larger than 3%. So your alternative test hypothesis is that the proportion is larger than this 1%. This is the reference value. If it goes beyond 3, you already want to have a power of 90%. So how many samples you need to make this calculation? So as always, you need to have two distributions. One when the null hypothesis is true, another one when the alternative is true. So when the null hypothesis is true, then we will take the upper bound. The upper bound is 1%. So let's say that you study, I don't know how many people. So you study, let's say 300 people. So with 300 people with this 1% of maximum value, this is the distribution you would expect. And if the alternative is true and it is 3%, then this is what we would expect to see. And then, as always, you need to find a critical value such that from that value to the right there is alpha, from that value to the left there is beta. That is what is explained in this equation. So from that value, that is x, that is the critical value, to the right there is alpha, and from that value x to the left, that is from 0 to x, in the alternative, that is beta. So now you have a full equation system from where you can solve for n and x. So with the given values, 1% and 3%, the solution is 390 and x equals 7. So that means that you will evaluate 390 people. If the number of individual 390 heavily using heavy users of the smartphone. If within this group the number of people with the Decker-Van syndrome is 7 or less, then you cannot reject the null hypothesis. So the null hypothesis is that there is a mistake here, is that the p-value is smaller than the reference. So as opposed to what we were doing with the previous examples of the sample calculation for the mean, for the variance, the critical value there, they were given by the distributions. That was also a critical value, but it was not explicitly returned by the method. So now we have explicitly returned a critical value, this x equals 7. And again, there are Gaussian approximations, and we see the same kind of formulas that we had before. So we have a term of the confidence level on the statistical power, the effect size, and it is normalized, and the normalization somehow goes up into the numerator. And here, if P0 and P1 are more or less equal, so they are more or less in the same range, then you can compute the average between the two, and this is the way to normalize. So there are simple formulas to calculate these kind of things. And for instance, in this example, the approximate formulas gives 366, one of them, the other one is given 420, and these numbers 366 and 420, they're pretty close to the exact solution 390. So we see that we have good approximations, and we should always make sure that the conditions for the Gaussian approximations are met. and in this case we're not meeting them. So one of the conditions was that n times the proportion was larger than 5, but we have a value that in both cases, in both approximations, they are smaller than 5. So we are not meeting them, but we are not far from the threshold, and then still the values are more or less in the same ballpark. Okay, so now let us construct proportion intervals when we have small populations, really small populations. So let's say that we have received in the lab a batch of 50 bottles of the same reagent, and we want to make sure that all the bottles are okay, so there are no defective bottles, or that the defective bottles is at most 2. So we are willing to accept up to 2 defective bottles. So how many do we need to expect to be sure that the number of defective bottles is at most 2 with a confidence level of 95%? So let's call S the number of defective bottles. So what we want to construct is a confidence interval such that the probability of this is larger than 95. So let's say that if we receive empty bottles, and out of which S are defective, and we want to observe, so we want to study N, the probability of observing X defective bottles here follows an hypergeometric distribution. This hypergeometric distribution is this one. So this is the number of defective, total number of defective, we observe X, and this is total number of bottles, out of which NT minus S are the ones that are not defective, and these are the ones that we observe. So we observe N minus X that are not defective, X that are defective. Okay, so we want to find N such that this is fulfilled, and again the smaller number is the smaller n is obtained for x equals 0. So we have simply to solve n here. So again, this is not an easy equation to solve manually, but it can be solved by a computer, and there are approximations. So if the number of bottles that we have to study is smaller than 10% of the total number of bottles, then this hypergeometric can be approximated by this binomial, and then we know how to calculate the sample size for the binomial. We did it in the previous example. So n should be larger than this. And there is another approximation that is called the approximation for rare events. So if the number of defects is smaller than 10% of the total, then the hypergeometric can be approximated by this. So you can see that the approximation is different. So this is n and then SU divided by NT. This is SU and then n divided by NT. But again, we have a binomial distribution, and we know how to compute the sample size for that. So it would be this one. Okay, so the solution. So the exact solution is 39. So this is the one calculated through this complicated way. And then we have the other two approximations. The one, a small sample approximation, give us 74, which is larger than the total number of bottles. But the problem is that we are violating the hypothesis of a small sample. So this n is not small compared to 50. And the other approximation, the one of rare events, is giving us 39. And this hypothesis is fulfilled because 2 is smaller than 10% of 50. So we see that approximations, again, they are pretty useful to make complicated calculations. Okay, so in our last case, we will compute, or we will design the sample size for making a test on a small proportion. So let's say that we have 212 tadpoles, and frogs are animals that decide their sex depending on the environment. So we wonder if half of them are female. How many of these 212 do we have to study to inspect this hypothesis? And we would like to have a 90% of power when the proportion of females is 65. So if it goes from 50, so our alternative hypothesis is that this larger, the proportion is larger than 50%. And if it reaches 65% or beyond, we want to already have a power of 90. Okay, so as always, we need to find a distribution such that I think we don't have it here, some graphical representation, but we need to find it is somehow similar to this, to the one we had before. So we have a null hypothesis, we have an alternative, we have to find a point. From that point to the right, it has to be alpha. The probability has to be alpha. From that point to the left, it has to be beta. And we have the same kind of equations that we had before. So this sum has to, so from that point to the right it has to be alpha, from that point to the left it has to be beta. So and you know everything, you have P0, P1, P0 is 50% in this example, P1 is 65%, and alpha and beta you also know, so you all only have to, and you know NT is the total number of animals in the pool, and in the we can use the approximation for a large sample. So for a large sample we already know how to compute it. It is 67, and because we know that 67 is a large fraction of the total pool, we can make the finite population correction. So we would have 52, and if you solve it exactly, so the exact solution is 64 and x 37. So we have 37 is the critical value. So 64 was already more or less in the same range as these approximations. Okay, so how to read this result? So you will analyze 64 tadpoles. If more than x equals 37 are female, then you reject the null hypothesis that the probability of being female is 0.5 or smaller. So this would be all for this first group of methods, and see you in the next video with the next group.